In this session, we're going to talk a bit about using integration and integrals to express volume of different shapes. And we'll come back to areas, but we'll get there a little bit roundabout. I'll start out with the basis that we're going to work from. This is kind of written on page 403 of your textbooks, but I'll mention it here. The volume of a solid of known integral cross-section area A of x. So what this means is A of x represents the cross-sectional area of a solid. And we can say that the volume would be equal to the integral from A to B. Oh, I'm doing good here. Hold on. The volume would be the integral from A to B of that area multiplied by dx. And I'm going to talk a little bit about what I mean by this. So let's say that I've got, and I'll go back to a nice linear function. And I'll just keep it simple in this case. I'll say I've got the line y equals x. But now let's say I take that line and I use it to make a cone. And I do that by rotating it about the x-axis. Yeah, looks somewhat like a cone. And let's say that I isolate at some point C a tiny little section of this cone. The area of this cross section would be the area of a circle, or pi times the radius squared, or in this case pi times c squared. If I then make that, say, instead of a circle, a tiny little cylinder with an infinitesimal width, I can then actually talk about the volume of that cylinder. I kind of wish I'd called that an x instead of a c. I think I will. That's an x. That's a pi x squared. Volume of the small cylinder would be the area of the base times the height times dx. Oh, why did I get an r there? Pi x squared dx. So what this gives me is the volume of this infinitesimally small cylinder. If I then say that that goes out to some point r, I could say that the volume would be the integral from 0 to r of pi x squared dx. If I do the integration, I get 1/3 pi x cubed integrated from 0 to r, or 1/3 pi r cubed will be the volume of that entire shape. Now you might remember the volume of a cone is 1/3 pi r squared h, but in this case, since this was the line y equals x, the height of my cone and the radius of my cone were the same thing. So if h equals r, I should have 1/3 pi r cubed, which is what that works out to. If you've got any shape going like this and you can express the cross-sectional area in terms of variable, then you can use that to work out a volume. And we'll do a few more examples with this that are a little bit more specific. So let's talk about example 1 from page 404, where we have a square-based pyramid. A pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross-section of the pyramid parallel to the base of the square. Find the volume of the pyramid. And I'm going to try to draw this, and I will probably do a horrible job with it. So I apologize for that. Oh yeah. Ain't pretty, but it's alright. There's a diagram in your textbook along with this example too, which looks somewhat similar. So out of distance 3, we've shown that we've got base or length and width of the base of this thing that are each 3. So at any value x, if I draw a square around that point, it should have side lengths x and x. So my volume is going to be for the integral from 0 to 3 of the area of the cross sections dx. If these cross sections are just squares with length x, then this is going to be integral from 0 to 3 x squared dx, or 1/3 x cubed evaluated between 0 and 3, or 9 cubic units. So as long as you can come up with some expression to represent the cross-sectional areas of the shape, you can use that to figure out a volume as well. There are a few different variations on this, and I'm not going to get into a lot of them. I'm going to stick with this sort of area of cross-sections. There is also another method referred to as cylindrical shells, which they do outline in a few other examples around this section of the textbook, but I'm not going to delve into that. This is example 3 on page 405, and they show you a graph in this which shows the region of space enclosed by y equals sine x and y equals cos x. And of course they're going to intersect at pi over 4 radians. Y equals cos x, y equals sine x. Now if I were to take this space and rotate it around the x-axis, it's terrible in the way that you could actually draw it, I would end up with this almost bowl shape with it's almost triangular inside. And I can talk about its volume in the same sort of way. Only the cross section of this shape is like the area of a washer. If I were to grab one particular washer out of this, the area of that washer would be the area of the outer circle minus the area of the inner circle. Or pi cos squared x minus sine squared x. And if you happen to remember your compound angle identities, this would be the same as pi times the cosine of 2x. So the volume of the shape that's made would be the integral from 0 to pi over 4 of the area, which is pi times the cosine of 2x dx. Pi is just a constant. The antiderivative of cosine would be sine. And I'd have 1/2 come out of there, evaluated between 0 and pi over 4. So the sine of, well, pi over 4 times 2 is pi over 2. The sine of pi over 2 is 1. So I get pi over 2 out of that. Sine of 0 is 0, and my volume is pi over 2 units cubed. Lastly, I will take a look at example 6. Off of page 407, where I've taken the shape made by the radical function y equals root x and rotated that shape around the x-axis. So the area of a cross section, since it will be circular, is going to be pi times root x squared, or pi x. Yes, in the example this comes out to 4 here. So my volume would be the integral from 0 to 4 pi x dx. And just to be clear, so what you're doing here, pi x is giving you one of the cross-sectional areas. Multiplying that by dx is making it this little infinitesimally wide cylinder. And then the integral is basically adding up all those little tiny cylinders over the entire shape to give you the volume. So my antiderivative there would be 1/2 pi x squared between 0 and 4. The 0 wouldn't contribute anything, and I'd be left with 8 pi units cubed. Alright, and those are a few examples of one way you can use integration to find the volume of a shape, of somewhat more complex shapes than we have dealt with in the past. Usually the trickiest part is coming up with this expression for the cross-sectional area. Once you do that, you just follow that general pattern, the integral over the domain needed of that cross-sectional area times dx. Alright, that is about all I have to say about volume for our last session, which I should record later this week. I'll talk a little bit about some future things that you might see in calculus, although this ends the material for the course. Alright, that's that. Thanks for watching.